The next thing we're going to talk about is we're going to look at a little bit more detail about ionic compounds, how we determine their formulas, and how we name them. One thing I want to stress is that it is so important to get formulas right. If you change even a seemingly tiny part of the formula, you change the substance you're talking about. And that's why I enjoy this joke so much, because it shows that just a tiny change can make a big difference. So 2 men order drinks. The first man says, "I'd like H2O." The second man says, "I'd like H2O too." The second man died. I know jokes get less funny when you explain them, but just let me explain. This is water, H2O. But when you say H2O2, this is the formula for hydrogen peroxide. And while this is a useful chemical to use to clean wounds and things like that, you may have some in your medicine cabinet at home, it is toxic. So changing just a tiny part of the formula, just having a number here or not having a number in that position next to the oxygen, totally changes the substance that we're talking about. So it is important when we're writing formulas. There's no such thing as close enough when you're writing a formula. You have to write it very precisely. There's a definite right and a wrong answer. So let's look at how we write formulas and name ionic compounds. First, just as a quick refresher, an ionic compound is a compound composed of positive and negative ions. In an ionic compound, the positive and negative charges must be equal. They must be equal to each other so that the total charge of the compound is 0. Another vocabulary term we're going to need is the formula unit. The formula unit is the lowest whole number ratio of ions in an ionic compound that balances their charges. For instance, magnesium chloride here has the formula MgCl2, and we'll see why these charges balance out in today's lesson. But what's important is that you don't give me the formula Mg2Cl4. This is not the lowest whole number ratio. So we don't write this version of the formula. We write this version of the formula unit. So earlier this semester, we learned how to draw Lewis structures for individual atoms. We're going to start learning how to draw Lewis structures for compounds. And in an ionic compound, we're going to use these Lewis dot structures to show the transfer of electrons, the transfer of valence electrons from one atom to another. So here we can see that sodium has 1 valence electron and chlorine has 7 valence electrons. So what happens is sodium readily gives up its 1 valence electron, and chlorine readily accepts that 1 valence electron. So then we're left with sodium with a charge of +1 and chloride with a charge of -1. And this is our sodium chloride substance. Again, just to relate this to that kind of joke at the beginning of the slide presentation, sodium metal is incredibly reactive, would be incredibly hazardous to eat. Chlorine is a toxic gas, would be incredibly harmful to breathe. But when they react together and create their ions, these ions have different properties than the substances that they come from. And sodium chloride, you eat it all the time. This is table salt that you would put on your food. So formulas are important. Different formulas, substances with different formulas have different properties. Okay, remember an ion is an atom with a charge. A cation is a positive ion from losing 1 or more electrons. And metal ions tend to be cations, so they tend to have that positive charge. An anion is a negative ion from gaining 1 or more electrons. And nonmetal ions are usually the anion in a formula. one more reminder before we get started. I want to remind you that each corner around an element symbol has a meaning. We first learned about this when we talked about nuclear reactions, but each of these corners, top left, top right, bottom right, has a different meaning. So let's just remind ourselves what those meanings are. Around the element symbol, the top left gives us the mass number, the bottom left gives us the atomic number, the top right gives us the charge, and the bottom right gives us the number of atoms. And we're going to be doing a lot with the charge and the number of atoms today. So those are kind of the two positions that we'll be using. Okay, so for magnesium oxide, how do we go about drawing this Lewis structure? Well, magnesium atoms have 2 valence electrons, 1, 2. And oxygen atoms have 6 valence electrons, 1, 2, 3, 4, 5, 6. When magnesium gets together with oxygen, magnesium loses its 2 electrons, and oxygen conveniently has space to gain those 2 electrons. Remember, we're looking for a maximum of 8 valence electrons. And so what we get here is we end up with magnesium with 0 valence electrons. It actually has 8 valence electrons in the lower shell, but we just draw with 0 to show that it lost some electrons. And it now has a charge of +2. And now we have oxygen with 1, 2, 3, 4, 5, 6, 7, 8 electrons, and it has a charge of -2. So this is showing how ionic bonding works with losing and gaining electrons. Notice that we put the ions in square brackets with the charge outside of the brackets. You don't have to draw your electrons having a different shape. I like to do it because it helps me keep track of which electrons were originally on the oxygen and which electrons were gained later. Let's do the same thing with calcium chloride. Here we have calcium with its 2 valence electrons, and we've got chlorine. Oh, this time we've got 2 chlorines. So let me draw 2 chlorines, each with 1, 2, 3, 4, 5, 6, 7 electrons. 1, 2, 3, 4, 5, 6, 7 electrons. And what's going to happen here is I'm going to take this electron and put it on that chlorine. Now this chlorine has a full octet. It's full. It cannot accept any more electrons. But I have another chlorine here that can accept this other electron. And now we end up with a calcium ion that has a charge of +2 and 2 chloride ions that each have a charge of -1. And we don't have to write the 1 there. I just did. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8 electrons. So the reason we needed 2 chlorines here is because each chlorine only had room to accept 1 electron, but calcium wanted to give up 2 electrons. So I needed 2 chlorines around. 1 chlorine could accept 1 electron, and the other chlorine could accept the other electron. The last example we'll do in detail is potassium nitride, where potassium has 1 valence electron, but we have 3 of them. And nitrogen has 5 valence electrons. And now this potassium gives up its electron, and nitrogen is here to accept it. Now this potassium has a full valence shell, but nitrogen doesn't have a full valence shell yet, so another potassium donates its electron. This potassium is happy with its full valence shell, but nitrogen still can accept 1 more, which is convenient because I have another potassium here. And now I have potassium with a charge of +1, and I have nitrogen with a charge of -3. And rather than drawing out 3 of my potassiums again, it is acceptable to put a subscript here to say that you've got 3 potassium ions. Try these 2 for yourself. You can pause the video and then resume it. Sodium has a charge of +1. Oxygen has a charge of -2. So for this example, I'm going to need 2 sodiums for 1 oxygen, because my 1 oxygen needs 2 electrons to have a full valence shell, and that needs to come from 2 separate sodium ions, because each sodium atom only has 1 electron to donate. And similarly, between aluminum and chlorine, aluminum forms ions with a charge of +3. Chlorine forms ions with a charge of -1. Aluminum is going to want to lose 3 electrons, and so I'm going to need 3 chlorines around, because each chlorine will only accept 1 electron. So one electron goes to one chlorine, another electron goes to a second chlorine, the third electron goes to a third chlorine, and I end up with aluminum with a charge of +3 and each chlorine with a charge of -1, but I have 3 of them.